So I had done things in the wrong order the other day in class. So the first thing is to talk about conservation of potential vorticity in the shallow water model. And this is completely independent of the idea of having a stream function, and that was what got confused the other day in class. So let's write down the shallow water equations. This is du by dt minus fv is equal to minus g d by dx of h plus b dv by dt, and these are total derivatives, and so they include the advection terms as minus g d by dy of h plus b, and then d by d partial d by dt of h plus d by dx of hu plus d by dy of hv is equal to 0, where recall you've got a sloping bottom which is given by z is equal to b of x and y, and then you've got a free surface top which is given by z is equal to h of x, y, and t, and then you've got some kind of characteristic height here, big H, and you think of B as maybe you know, just sort of a little bit above the bottom, and then it extends up to H, which might be something like the average of the surface H of xt. So d by dt here in the first and second equations is not the partial of d with respect to t, and it's also not the full advective derivative because the w term is missing. Okay, so from this we conclude the vorticity equations, and you get this by differentiating the first equation with respect to y, the second equation with respect to x, and subtracting the first equation from the second equation. So this step is exactly as it is in the notes. If we have zeta now is equal to vx minus uy, then subtracting the first equation from the second after applying these partial derivatives leads to this, d zeta by dt, that's the partial of zeta with respect to t, plus zeta times ux plus zeta times vy plus u times d zeta by dx, right, plus v times d zeta by dy. Sorry, sometimes I'm writing u sub x for the partial of u with respect to x and so on. It's slightly arbitrary, but it's just I've used the partials in the definition of the vorticity, so it seems to be fairly natural. So plus u times f sub x plus v times f sub y plus f times ux plus vy is equal to 0. Recall that everything cancels on the right-hand side because of the inequality of mixed partial derivatives. So h, which is what is replacing the sort of pressure term, the height replaces the pressure inside the shallow water equations, actually completely disappears. So now what we see is that we actually have a full total derivative, including advection, for the vorticity coming from these terms here, right? Plus we get terms which are like zeta times ux plus vy coming from this, and f times ux plus vy. We also notice, though, that this piece here, ufx plus vfy, looks like the sort of terms you would get from advecting f and y, although f itself does not depend on t. So in fact we could think of this as the total advective derivative of t. Alright, so this implies that what we get then is the total derivative of zeta plus t plus the total derivative of f with respect to t, because the partial of f with respect to t is equal to 0, plus zeta plus f times ux plus vy is equal to 0. Right? In other words, what we've got is we've got the total derivative of zeta plus f plus ux plus vy times zeta plus f is equal to 0. So we actually have a nice equation for the quantity zeta plus f. We now use the third equation, which was the equation for h, to replace this ux plus vy. And this is the point where I kind of made out that there was something strange going on, because we had actually assumed ux plus vy was equal to 0, but this is completely independent of assuming that ux plus vy is equal to 0, and this just comes from the shallow water equation. So if we rewrite the third equation, you can see that that actually can be written as the total derivative of h with respect to t plus h times ux plus vy is equal to 0. So that's what the third equation is, which implies that ux plus vy is actually equal to minus 1 over h times the total derivative of h with respect to t. So we can now put these two equations together, this one here for ux plus vy, together with this equation here, and we can get a nice complete equation for the derivative of the potential vorticity. So putting those two equations together from the previous slide, we have d by dt of zeta plus f plus zeta plus f times this ux plus vy. We now replace that with minus 1 over h, total derivative of h with respect to t, and that is equal to 0. But this can now be rewritten if you think about it. This is just says that the total derivative of zeta plus f over h is equal to 0. And this expression here is the potential vorticity of the shallow water model. Right? And we see that this has absolutely nothing to do with assuming that u and v are given in terms of a stream function. That's a completely independent issue, which I'll discuss in the next short video.